guys? So we're actually starting the physics unit, not like yesterday where it was just a fake start because I forgot you had the research project yesterday. Okay, so the research project, guys, is due Friday of next week. Yeah, or Thursday or Friday. 29th, okay, so Friday of next week. So you got a while on that, but again, don't leave it till the last minute. Okay, manage your time and manage your time and make sure that you are, picking away at it a little bit at a time so you don't end up having to, sit down and work on it for a 3-hour stint. Okay, you've already had like 2.5 hours of class time to work on it, so just make sure you're staying on top of it. Okay, so for the physics unit, okay, one of the big themes in physics is energy. All right, I mean, energy's kind of been in every unit, but it's really big in this one. Okay, specifically, we're going to be looking at mechanical energy. We'll talk about other kinds of energy, okay? And that's kind of what we're going to be looking at today is all the different forms of energy. But the most important form of energy in this unit is mechanical energy. Okay? You have mechanical energy if you have the ability to do work. All right? And by work, I mean that you could lift something or you could push something. You could do something that would transfer energy from you to something else. That's what work is, transferring energy from you to something else. Okay, so we'll be focusing mostly on mechanical energy in this unit, but like I say, today we're going to look at all forms of energy because they all have something in common. Okay, and that is the idea of what energy is. Okay, all forms of energy have the ability to transfer or transform. Okay, they can be transferred from one object or system to another, or they can transform from one type of energy to another. Right? If a ball rolls down a hill, okay, at the top of the hill, it has potential energy. It isn't moving, but it's above the ground, and it has the potential to roll downhill. Okay, so it has potential energy. If I allow it to roll downhill, that potential energy changes. It turns into kinetic energy. The ball moves faster and faster and faster as it rolls down the hill. Okay, at the bottom, all of its energy is now kinetic. And if that ball hits something, it'll transfer that kinetic energy to that object. In that transfer, some of the kinetic energy will be turned into other forms. Like usually when one thing hits something else, we hear sound. Sound's a form of energy. Okay? When something hits something else, usually some heat is generated. Okay? Heat is thermal energy. Okay? Thermal energy is a type of energy. So all of these things can be turned from one form to another, or they can be transferred from one object to another. All right. Example we have here is the Inuit blanket toss. Okay. If you can imagine in the tundra, okay, the very far north of Canada, okay, in the tundra there are no trees. Okay. The tundra is really an Arctic prairie. So imagine Saskatchewan but colder. Okay, southern Saskatchewan but colder. Okay. It's very, very flat and it's featureless essentially. So you can only see to the horizon. And prey knows when you're coming because they can see the same distance. Chase, can I get you to close that for me, please? So it's very hard to hunt large game like caribou and things like that. Okay, so what they do instead is to see further, they gather everybody around, grab onto a blanket, put the smallest person on the blanket, and throw them up in the air. Okay? There's no trees to climb, no hills to climb so that you can see further. The only way to see further is to throw someone up in the air and have them look around. Okay, so that's what they do. Now, to throw someone up in the air requires energy. Okay, they're initially getting that energy in the form of chemical energy, the food they have eaten. Okay, their body digests it, turns it into other forms of chemical energy, and that chemical energy is transformed into mechanical energy when their muscles contract. Okay, so when they pull up on the blanket, okay, they're turning chemical energy into mechanical energy and transferring that energy to the blanket, and the blanket is transferring the energy to the person sitting on the blanket, and they are thrown upwards into the air. Okay, they're given a lot of kinetic energy, and as they go up, their kinetic energy decreases and their potential energy increases until they're at their highest point. Okay, so it's just an example of turning one form of energy into another. Okay, here's the problem with the idea of energy. You can't measure it. Okay? Energy isn't matter. And that was always the problem with it, is everyone was trying to say, well, energy works like this. Energy is this. Energy is that. But all the comparisons or all the analogies they made were that energy was some form of matter. Okay? And energy isn't matter. Okay? I have the same mass regardless of whether I am standing at the bottom of a staircase or the top of a staircase. But I have way more energy at the top of the staircase. Energy isn't matter. If increasing energy was, or energy, sorry, was a form of matter, then when I get to the top of a staircase, there should be more of me. Okay? Like I should get bigger as a result of getting more energy, which of course doesn't happen. Okay? So the problem with this idea of energy was that no one could say, here's some, measure it, or look at what it can do. It was hard to do that because energy wasn't a material. Okay? It's just there. It's something that you can possess but not really show. Okay? All right. So the definition of what energy is, okay, when we think about what energy is, we think of all the examples of energy that we've seen. A lightning bolt, the sun, okay, fuel, like a campfire, things like that. Okay, we think of all these examples of different kinds of energy, right? Which is fine, as long as we understand that that particular material is not necessarily energy. It has properties that result in it having some energy. Okay. Okay, sorry, lost my place here. Okay, so different types of energy here. First one we'll look at chemical energy. We'll look at chemical energy first because, well, for us, for Albertans, it's the most important kind. Unfortunately, right now it's in the toilet, but okay, it'll come back. Chemical energy, okay, is the energy that is stored within the chemical bonds of a material. Right? So if we're looking at, let's say, gasoline. Okay? Gasoline, the active ingredient in gasoline, is called octane. If you've ever filled up your car with gas, okay, there's 3 different grades of fuel that you can put in your car, right? Regular, mid-grade, and premium. Okay? And they have different numbers on them. Sorry, it's taking me forever to draw octane, but this is what it looks like. Okay, I probably should have drawn propane. It's shorter. But. Okay, now, the active ingredient is octane. It's called octane because it's got 8 carbon atoms in the chain. Okay, every place where there's a chemical bond, these little lines here, okay, energy is stored. If I break that bond, energy will be released. We break those bonds by burning fuel. Okay? If you react it with oxygen, those bonds break. Okay? And we saw in the chemistry unit that this plus oxygen will produce those 2 things. So essentially, I break every single bond that is in that molecule and rearrange them so that I form new materials that have lower energy. Okay? Carbon dioxide and water have way lower energy than octane and oxygen do. Which is why I can't do very much with these 2 things in terms of powering anything. Right? Sure, they're the raw materials for plants to use to carry out photosynthesis, but what do plants have to add to this in order to carry out photosynthesis? Light energy, right? They got to add energy to it in order to go back to making something like this. Okay? All right, so chemical energy is anything that has chemical bonds that can be broken to release energy. Hydrocarbons like octane are prime examples of that. Propane is another one. Okay, C3H8, so it's just got 3 carbons. Okay, so it's got H's. Okay, like this. Okay, it's got an H at every one of those spots. Anything that can burn, okay, has chemical energy. Everyone all right with that? Okay. Now, do some things have more chemical energy than others? Yeah. Octane burns hotter than propane does. Okay? Which is why we use octane to power vehicles. Now, are there propane-powered vehicles? Yes, but you lose power when you go to propane. Okay? Because it doesn't burn as hot. Okay? So you use a lot more of it. Okay? Some vehicles can run on what's called E85 ethanol blended fuel. Okay? It's got alcohol in it, ethanol. Okay? Ethanol has 2 carbons in it, and then some other bonds like an OH group and things like that. It's not as energetic a molecule. which is why it doesn't burn quite as hot. Okay, E85 ethanol fuel, I don't think there's even a place where you can get it in Canada. Okay, but it's big in the United States. But some vehicles can burn it. Okay, it doesn't burn as hot. You don't get nearly as good a gas mileage or power when you are using that fuel. It's not as energetic. Okay, the person who discovered this, okay, the alchemists kind of discovered this a little bit. Okay, but further on to that, Antoine Lavoisier did some experiments where he took equal masses of different fuels, burned them, and recorded how much they could change the temperature of a certain volume of water. Okay, and he found that some fuels could change the temperature of the water a lot more than other fuels. For example, wood could change the temperature of water by a certain amount, but if you put coal in there, same amount of coal, it got way hotter. Okay? Coal possessed more hidden secrets, okay, as the alchemists would have called them, okay, than other types of fuel did. All right, so the big thing here, guys, for chemical energy, okay, is that chemical energy is a form of potential energy, okay, that is stored in the chemical bonds of compounds. Okay, that's the key thing we need to understand about chemical energy. So when we eat food, okay, we're taking in chemical energy. Our body is going to break that down in the mitochondria, okay, and turn it into thermal energy or other forms of mechanical energy, okay, and we'll go from there. Okay, chemical energy can be turned into, like we said, thermal energy. That's the most common way. Okay, that's the way we generate electricity for the most part in Alberta. Okay. What's the #1 way to generate electricity in Alberta? Nope. Nope. Coal. Okay? We use coal as our #1 way to generate electricity. Oil and gas are second. Okay? We have upgraders, they're called, that burn oil and gas to produce electricity. But coal is still the #1 fuel for generating electricity because it's cheap and we got lots of it. Okay? So what are the drawbacks of coal? Well, it produces a lot of carbon dioxide. So does anything you burn, okay? But it produces a little more and kind of sooty smoke, kind of darker black smoke. But it's good for generating electricity because we can use the heat it produces to turn water into steam. Steam turns a turbine, generates electricity. Works really good. Okay? Eventually, what we need to do with chemical energy is take its potential energy, turn it into thermal energy, and turn that into mechanical energy, turning a turbine, and then turn that into electricity. Okay? Here's the problem with that. Every time you turn energy from one form to another, you lose some. All right? So the more directly you can convert one form of energy to another, the more efficient that will be. Okay? Wind power is pretty efficient. You take mechanical energy, the wind, and you turn it directly into electricity. Okay? The mechanical energy of the turning turbine, okay, the wind turbine, directly attaches to the generator, which makes electricity. Okay? Way more efficient. What's the drawback of wind power? You got to have a place where it's windy. That's why they're all down there in Pincher Creek. Okay? It's pretty much always windy down there, but not every day. Okay? So it's not a steady form like coal. Well, you need a little more electricity, shove a little more coal in there. Okay? You can't just go, hey, come on, wind, need some power. Okay? It doesn't work that way. Right? So it's not as reliable. Okay? And one coal-fired plant can generate a lot of electricity. One wind turbine, not as much. So you need to have lots of them. And that means you have to look at them. Right? You got to build them somewhere, and not everybody wants wind turbines on their property. Okay? Because, yeah, well, it's loud, too. If you've ever stood next to one when it's spinning, it's like standing next to an airplane. Okay? It's loud. It's a big spinning propeller. Okay? So it makes a lot of noise. Right? The other drawback, apparently they kill a lot of birds. Yeah, right? This was the thing that really choked the Alberta government when they started that whole project. Like, oh, come on, all the Greenpeace people were like, come on, you got to get away from all these fossil fuels. You got to build all these environmentally friendly wind turbines. They build all these environmentally friendly wind turbines. The same people come back 10 years later. Can you see all the birds you're killing? It's like, what do you want from me? Right? Come on, I built you these nice clean things, and now dumb birds are getting killed. Like, there's no pleasing you. So, yeah, there's always a drawback to everything. Apparently birds get confused by the sound these things make, and they fly into the propeller blades. Yeah. It can't be that many birds. I mean, but apparently there are some birds. So, yeah. Okay, the other problem with wind turbines is maintenance. They do have to be regularly maintained and things like that, and if you don't, they actually start on fire. Yeah, so they're good though. They're good in that they're clean as long as they don't start on fire or kill birds. But okay, they are clean. There's virtually no emissions from a wind turbine. Okay, but there's always a drawback, right? It's nice and clean, but I can't count on it all the time. Okay, electrical energy and magnetism. Okay, sorry, before I go to electrical energy and magnetism. First example of a device that converted chemical energy into electrical energy. Okay, this is the Volta pile. Okay, it was developed by a guy named Alessandro Volta, an Italian scientist. Okay, and what he discovered was if he had different metals stacked on top of each other, there was a potential difference between the metals. That is, electrons would want to flow from one metal to the other naturally. And if you have electrons flowing, that's electricity. If you put something in there that can convert the kinetic energy of electrons into something else, it can power it. Right? And that's what all of our electrical devices do. Okay? As electrons rush through the wires of our electrical devices, they're caught, okay, by other things, and their energy then turns or converts into some other form, okay, and we harness that. Okay? That's what electrical energy is. So the Volta pile converted chemical energy into electrical energy directly. This is the ancestor of all batteries. Okay? The ancient great-great-great-grandfather of all batteries. Okay? Was this rechargeable? No. Okay? Rechargeable batteries obviously require certain metals that can lose electrons and then have them given back, okay, in the same way. Charging rechargeable batteries. Is it ever as fast as discharging? Never. Okay? You can never charge a rechargeable battery, at least not without damaging it in some way, okay, as fast as you can discharge it. Okay? It has to go in slow. You have to essentially cause a chemical reaction to flow in reverse. Okay, in order to recharge a battery, you have to have a reversible chemical reaction where when putting electrons back into it, you'll regain the materials you had at the beginning. Okay, so electricity or electrical energy is work done by moving charges, specifically electrons. Okay, why does it have to be electrons? Why can't it be protons? Because electrons can move. Protons are in the nucleus of an atom, and last time I checked, full-on atoms don't migrate through wires. Okay, that would be very difficult to do. Right? But electrons can flow through wires because essentially all they do is jump from one atom to another, okay, as they run through. Some things are better able to conduct that than others. Okay, copper is a good conductor. Silver is even better. Okay, but it's expensive. Yeah, you don't see too many machines with silver wires. All right, so the Volta pile, okay, is stacked layers of two different metals, such as copper and silver, moistened with paper sandwiched between each layer. Okay, if you connect the wires from the negative end to the positive end, then a current will flow. Okay, everybody with me there? The negative end is where the electrons come out. Okay, the positive end is where they go back in. All right, so the electrons can flow, okay, but every time an electron goes through this wire and whatever it's attached to, it slows down just a little. Okay, doesn't mean it stops, it comes back, but eventually they lose that energy, and that's what weakens the battery as it goes along. Okay, the electrons just get slower and slower, they have less and less energy as that reaction goes on. Okay, so we already talked about Volta. Okay, now, once we started realizing that electrons could flow, we started discovering all the things electrons do when they flow. Okay? Electricity and magnetism are really connected to each other. One can cause the other. Right? If I have flowing electricity, that's going to produce not only an electric field, but also a magnetic field. Okay? Lots of people were, for the longest time, worried about living near big like wire towers, that had a whole bunch of, the big power towers that had all kinds of wires on them, because they were afraid about the magnetic fields that would be generated by these high voltage lines, okay, that were running near their house. The reality of it is that yes, electricity produces magnetic fields, but magnetic field strength decreases exponentially as you get away from the wire. Okay, like so much so, like you basically wouldn't be able to even measure it if you were more than about 100 meters away. Okay. Now, that means, though, if you were standing right underneath it with your cell phone, you might have some trouble. okay? Because the magnetic field, then you're quite a bit closer to it, and it could disrupt the magnetic field your phone is producing in order to transmit information, okay? So the idea of having electromagnetic waves, radio, okay, results from us being able to manipulate electric and magnetic fields within the transmitter of your phone. All right, first discovery of this idea that electrons cause magnetic, or electricity causes magnetic effects, was done by Ørsted. Okay, that's a name you probably want to know. Okay, Ørsted showed that electricity had magnetic effects by accident. He had a compass lying around, and he was doing an experiment with current-carrying wires, whatever it was. Okay, and he noticed that every time the current flowed through the wire, the compass would orient parallel to the wire. Okay, it wouldn't point north. As soon as this thing was carrying electricity, the compass would orient so that it was this way. Okay, parallel to the electric current. As soon as he turned off the electricity, it would go right back to north. Okay, the only way that that can happen is if there's a magnetic field surrounding our electric current carrying wire. Essentially, he discovered a way to build the first electromagnet. Okay. If you've ever built an electromagnet, all you do is you take a piece of iron and you wrap copper wire around it really, really tight, okay? And then hook both ends to a battery, and you got yourself an electromagnet, right? Because the magnetic properties of the iron are magnified by the magnetic field produced by the current-carrying wire. You get a really strong magnetic effect. Okay? Now, once that was discovered, it goes the other way. Magnetism, magnetic fields, can push electrons. Okay, so what a guy named Faraday did is he developed the first electric generator, okay, by finding that if he made a coil of wire and pushed a magnet into it, he could push the electrons through the wire and generate an electric current, because what are moving electrons? Electricity. Okay, so pushing a magnet through this wire would get the electrons moving. Now, of course, the magnet has to keep moving. You can't just stick a magnet in a coil of wire and go, magic, I've got electricity, okay? Because then you'd be creating energy from nothing. But if the magnet is constantly moving, it will constantly be moving the electrons. So essentially what he had was a generator that could move the magnet in and out of the coil of wire, producing an alternating current, AC. Okay? Which is what we use for electricity now, right? Most of your devices convert the alternating current to direct current, but okay, for the most part they use electric or alternating current. Okay, and that's what he developed. So magnetism can produce electric effects. Electricity can produce magnetic effects. Everybody good with that? Okay, so no Ørsted and Faraday. Okay, they're important guys. All right. Now, as this relationship started to be discovered, people thought, okay, so essentially what we're saying here is that energy is really fluid. Fluid in that I can change it into whatever kind of energy I want. Okay? If I have one kind of energy but I want another, all I have to do is find a way to convert it. Okay? So a guy named Seebeck said, well, thermal energy is always readily available. Right? There's always heat around. If I start a fire, I've got heat. So I want to turn heat directly into electricity. There's one problem with that. Turning heat into anything is really inefficient. Heat or thermal energy is the lowest form of energy. It's always produced as a waste product. Okay? So if I have lots of it, I might be able to make other forms of energy. What Seebeck produced was the first thermocouple, okay? A device that converts heat directly to electricity. That conversion is very inefficient. Right? You need tons of heat to even get a small amount of electricity, but it works. And in fact, it works so well that thermocouples are embedded in the brake rotors of hybrid cars. Okay? Anybody have a hybrid car? Okay? Anyone know what a hybrid car is? Okay? They're ones that have a gasoline and an electric motor. Okay? Now, hybrid cars, when you're braking, okay, so you squeeze the brake pads against the brake rotor. That generates a lot of heat. It essentially turns your kinetic energy of movement into heat. Okay? Well, what happens is the heat in the rotor goes to the thermocouple and turns some of that heat, not much of it, but some of it, back into electricity, which recharges the battery. Okay? Makes it even more efficient. Okay? Because using an electric motor is way more efficient than using a gas-powered motor. Right? Electric motors are oodles and gobs way more efficient than a gas-powered motor. Okay? They're just it's hard to make them work like a gas motor, okay, which is why hybrid vehicles and electric vehicles are not catching on, okay. The other problem is range, okay. If you run out of gas, you fill the gas tank, you go again. Okay? You run out of electricity, you park plugged in for hours, and then you go again. Okay? It's not as convenient. Okay? So that's why kind of electric vehicles, even though they are way more efficient, are not catching on. Okay? They simply don't have that ability yet. They're getting there. The new Tesla, you can plug in at a quick charge station and have it charged now in under a half an hour. Okay? Which I mean is still longer than fill up the car with gas, but they're really expensive. Okay? All right, so what Seebeck did to show that you could convert heat directly to electricity is he set up Ørsted's experiment. Okay? He said, if I have a compass needle and a wire running over it, and electricity runs through that wire, the compass needle will change directions. So what he did is he took some iron and some copper, and he heated up the iron. Now, when you heat up iron, it heats up a lot slower than copper does. Okay, so the energy naturally wanted to go into the copper wire ahead of going into the iron bar. Okay, so what he got was movements of particles back and forth because he was heating it up. Those movements of particles essentially were transformed into moving electrons as they went through the copper bar here, and he generated enough electricity that way to get the compass needle to go parallel to his copper bar. All right, so he proved, yes, I can make electricity from heat, but he also proved it doesn't work very well. It's possible, but it's not great, right? It's not like we want to have a whole bunch of fires trying to directly generate electricity. That's not efficient, okay? Using heat like burning coal with a turbine and water, that's quite a bit more efficient than this, okay? Because where does the majority of your heat go in this situation? Well, actually into the surroundings, right? Like, yes, certainly you've got the flame against the iron here, but you've got heat radiating everywhere outwards from that candle, right? You're not capturing it all like you are with a boiler and a big, you know, kind of coal-fired fire underneath that boiler, right? You're capturing way more of the heat in that situation. All right. Right, we already talked about that. Okay, now Thomas Edison, what did he do? He made the light bulb, okay? He's famous for being what a lot of people called the most successful failure, okay, in American history. Okay? He was actually once asked, did you ever think at any point that you were a failure because you couldn't build the light bulb? Because he tried basically a couple of thousand different ways to build a light bulb, and they didn't work. And then finally he got it right, and it worked. He said, did you ever consider yourself a failure? And he said, no, I found out about 1,000 different ways to not make a light bulb. That's totally a glass half full kind of guy, okay, on something like that. But okay, what does a light bulb do? The kind that Edison built. Right, uses heat to make light. How does it make the heat? From electricity. Okay, so it runs electricity through tungsten, which is a very poor conductor. That gets really, really hot. It glows white hot. That's what gives you your light. Okay, most of the energy used by that kind of light bulb makes heat. It makes very little light energy compared to the amount of electricity it uses to do it, okay? Because most of it is generated as heat. All right, nuclear and solar energy. Okay, the idea of how the sun makes energy wasn't discovered until quite a bit more recently than you might think, because you know, for thousands of years, people looked up at the sun and went, "Oh God, that's bright." Oh, come on, you guys. Okay. But when they looked at it, okay, not for very long, obviously, okay, it looked like a big fire. And it is, but it's not a campfire, okay? And unfortunately, when people look at fire, fire's fire, they didn't know there's different kinds of, there's chemical fire and there's nuclear fire, okay? The sun is a nuclear fire, not a chemical fire, right? But for the longest time, people didn't really understand the difference. They didn't know about nuclear power. So they figured that the sun must just be a giant fire in space. Okay. Now there's a couple of problems with that. Fire doesn't burn in space because there's no oxygen. Okay. And secondly, if that was the case, the entire mass of the sun would be consumed in under 5,000 years, because a chemical fire, to produce the amount of heat that the sun produces with a chemical fire, would go through energy a lot more quickly than it does using nuclear fusion. Right? So nuclear energy is it's a form of potential energy stored in the nucleus of an atom. Okay? If I change the nucleus of an atom, and we talked about this in Unit 1, I will release some of that energy. Okay? So when the nucleus of two atoms are split, which is nuclear fission, I release energy. Okay? Or when the nuclei of two atoms combine, that's fusion, energy is also released. Okay? Because in both cases, I am altering the atom itself. Okay? Now, the form of nuclear energy we use most often here on Earth is fission. Fission is far more controllable, okay? But it doesn't generate as much heat as fusion does. But again, we want the control part of it. It's kind of important to know how fast your nuclear reaction is going to occur. Okay? If it occurs faster than you want, you have problems. Okay? So fission reaction we control in a nuclear reactor. I think I showed you this with the fuel rods back in Unit 1, right? Okay? You lower the fuel rods into the path of like neutrons that are being shot at them. The neutrons break the atoms and that releases the energy. Okay? Within the sun, the source of nuclear fire there is different. It's nuclear fusion. Oh, okay. Okay. So within the sun, okay, we've got all of this hydrogen. The sun is almost entirely hydrogen and helium. Okay? The reason it's got some helium is because it's making helium all the time. The sun is huge, like mind-bogglingly huge, millions of times bigger than the Earth. Okay? Because it is so big, it has a tremendous amount of gravity. So much gravity that within the core of the sun, okay, hydrogen atoms are forced together so hard that they actually fuse. Okay? The two atoms are forced together and they become one helium atom. Okay? Each time that happens, tons of energy are released. Not with each atom, okay? But that's going on all the time, and it's going on at a high rate because there's so much hydrogen in the sun. Okay? So lots and lots of energy is released every second by this forcing together of atoms. Okay? That's nuclear fusion. That's the source of power for the sun. That's why the sun looks like it's on fire, even though it's in space. Okay? A nuclear fire does not require oxygen in order to burn. Okay? Everybody follow me there? Right? So nuclear fusion, at least the power of the sun, is really the result of incredibly large amounts of mass making lots of gravity that force things together. Okay? The Earth doesn't generate any fusion because it's not heavy enough to force atoms together. Okay? Can we make atoms go together? Yeah. Okay? We can. Under certain kind of controlled circumstances, we can cause nuclear fusion to happen. The first atomic bombs were hydrogen bombs. They caused hydrogen-hydrogen fusion reactions. Okay? So they made nuclear fire that way. All right. So, like we said, originally scientists thought the source of energy on the sun was chemical energy from burning, but it would have only lasted about 5,000 years, and obviously our sun has been burning for over 5 billion years, okay? And will continue to burn reliably for probably another 3 to 4 billion years, and then it'll start having some trouble, okay? Because it'll run out of hydrogen, and it'll start to fuse helium. Well, not in the amounts it would require. I don't know where we'd get it from, right? But the problem with fusing helium, the sun will be able to do it for a little while, but it doesn't have enough mass to make that reaction go for very long, and so eventually it'll just stop. The helium won't fuse properly, and the sun will swell, okay, become like a kind of a red giant, and then it will collapse. Okay, it'll just come down to a white dwarf that doesn't produce very much energy because it's just run out of stuff that it's able to fuse. Okay, our sun's not going to blow up. Okay, our sun won't go supernova. It isn't big enough. Right, but it will eventually run out of fuel, and when it does that, it'll get big enough to swallow up all the inner planets, including us. Okay, and then it will just kind of fizzle out and collapse on itself. Okay, we best find a new place before that happens, but we got a few billion years to figure that out. Since we've only been around, you know, for maybe 100,000 years, I think we got a pretty good chance of figuring it out before then, as long as we don't poison the planet before then. Okay. All right, so solar energy, like we said, results from hydrogen-hydrogen nuclear fusion. Okay. That energy comes to the Earth in the form of electromagnetic waves, okay? Waves that can travel through the vacuum of space. X-rays, gamma rays, ultraviolet rays, okay? Visual light, the stuff that we can see, okay? Infrared waves, heat waves, okay? All of those travel through the vacuum of space to the Earth. Fortunately for us, the Earth blocks the majority of the short, harmful stuff. X-rays, gamma rays, and things like that. UV rays reasonably well, okay? But the really short stuff all gets deflected before it gets here. If it didn't, we would literally fry, okay, down here. Okay, motion and energy. Okay, so motion and energy, this has to do with the stuff we said was most important, okay? Motion and energy has to do with mechanical energy, okay? Now, Newton built this thing here called Newton's cradle. Okay, you know the clicking balls, right? And you pull one and they just go back and forth and keeps clicking. Okay, that nearly got Newton beheaded because they thought he was a witch. Yeah. Okay. Well, it was like magic, right? People didn't understand what was going on from a physical level. All they saw was that when he lifted the ball on one side and let it go, a ball on the other side went up. Okay. This is not something you do when people believe in witches, okay? Because it gets you in trouble. Whether you can explain how it works or not, a lot of people are not going to like what you have to say, and that's what happened to Newton, okay? He really had to do a lot of backpedaling and explaining so that people understood, look, what I'm doing isn't magic. It's physics. You do it. Oh, hell no, I ain't touching that. And then I'll be a witch. It's just you. If I touch that and it happens, then I'm a witch too, so I don't want to do it. Okay? So they didn't, okay? And that was kind of where it kind of broke down, or where he was able to prove to people, look, it doesn't have to be me. It can be anybody. And then they say, well, but that's just because you possess that thing because you're a witch. Right? There was always an argument that you could be a witch. Okay? It was a really bad time to be alive. Okay? Don't look at somebody funny, they'll think you're a witch. Okay? What do they do to witches? Cut their heads off, burn them at the stake, all kinds of awful ways to die. Okay? Put them in a bag full of rocks and throw them in the water and drown them. There was all kinds of horrible ways to die as a witch. Okay? Now, what's really going on here is what we call the WorkEnergy Theorem, which is the most important concept in not only this unit, but science in general. Because the WorkEnergy Theorem explains how energy can move from one place to another, okay? And how it can be transformed from one type to another. That's what Newton's cradle showed, okay? When Newton would pull this ball away from the others, he was doing work because he was transferring energy from himself to this ball. If this ball is in this position, it has no energy. It's not moving and it has no potential energy either. It's not going to do anything except hang there. Okay? But as soon as he pulls it away, he's lifted it a little bit. It now has the potential to fall back to that position. And when it does, the work he put into it will become kinetic energy. And when that hits this ball, that energy will be transferred to it, through it to this one, through it to this one, through it to this one. When it hits this one, there's nothing to stop it. It flies out on the other side because it's all the energy from the work Newton did in lifting the first ball ends up in the last one. And flies up because it's got energy and it's got to go somewhere. It's got to do work. Now, will that thing run forever? No, it eventually stops because it's inefficient. Every time a ball hits another ball, there's sound. Right, there's sound and heat, so eventually it stops because those are forms of energy that are being lost to the surroundings. Okay, but it's a great example, a simple example of one form of energy being turned into others and energy being transferred from one object to another. Okay, that's the WorkEnergy Theorem. Work is a change in energy. Okay, Newton changed the energy of that cradle by pulling one ball away, doing work. Does that make sense? Okay, so one of the most important discoveries in science, and as with all important discoveries, not always well accepted. Okay. A warlock, actually. A male witch is a warlock. Yeah. All right, so a couple things here, guys, in here that you'll probably want to underline, highlight, or whatever, okay, that are important, okay, is this idea of the two types of energy, okay, that are in the environment. That is kinetic energy, okay, that is possessed by any moving object. Any moving object has kinetic energy, all right? And potential energy, in this case gravitational potential energy, is possessed by any object that can fall, okay? That is essentially above ground level. Okay? And that's why it's hard to lift. That's why it's work to lift things. When you lift something, you're giving it energy from yourself, okay? So if you're lifting weights, okay, you're constantly doing work, giving the weights energy, and then you're taking that energy kind of back as you lower them, okay? So it takes energy to push it away, but it also takes energy to lower it, okay? Unless you just let it fall. That takes no work at all, but you die after, okay? Yeah. Well, if it falls on your neck, you do. Okay. Yeah. Right? So you lower it by pushing up on it, right? I don't pull down the weights. I push up on them when I lower them down. That's still work. Okay? Essentially, I'm letting those weights do work on me in those situations. All right. Now, these two things, kinetic and potential, combine to form mechanical energy. Okay? So the sum of the energy of motion and position is mechanical energy. In other words, write this down. Mechanical energy equals kinetic energy plus potential energy. EM, mechanical energy, equals EK, kinetic, plus EP, potential. Energy. Yeah. Mechanical energy is EM, kinetic energy, potential energy. Pardon me? Energy potential, yeah. E subscript P, right? It's not a little p, it's subscript, right? So like this, capital E and then like a tiny p, right? Subscript, E potential. Okay, now, unfortunately for us, we need to get the other forms of energy by using the type of energy that is most common, thermal energy, which we incorrectly call heat all the time, okay? But heat is actually the transfer of thermal energy. I feel heat when something hot is transferring thermal energy to me, okay? So heat is actually not a form of energy, it's a transfer of thermal energy from one object to another, okay? In the same way that work is a transfer of mechanical energy from one object to another, okay? Heat is something I feel because I'm gaining, okay, thermal energy. Okay, so the Greeks had, kind of some idea, a little bit of an idea about how energy worked, but not a really great one. Okay, Joseph Black was kind of the first person to kind of quantify all of this. He discovered, and this isn't like a rocket science, like, oh wow, this is amazing discovery. He discovered that when a cold object is placed in a cup of hot water and removed, the cold object would get warmer. I told you it wasn't rocket science, okay? But every discovery is important, okay? And in this case, this was an important discovery because it showed that energy flowed in only one direction, okay? Energy can only flow in one direction, from a high energy object to a low energy object. That's the only way it can go naturally. In the same way that in the last unit, materials would always go down their concentration gradient. Unless we put in energy, then we can make them go the other way, okay? Well, he discovered that energy flows from hot to cold or from high energy to low energy. So Joseph Black, okay, he made a pretty important discovery that was common sense, but, okay? Right? So he explained, this was where he went wrong, he explained that that was because there was an invisible fluid that flowed from the hot water into the rock, okay? They called this fluid caloric, okay? They had a name for it. That's where the word calorie comes from, okay? But there was this invisible fluid that flowed from one place to another. The problem with that explanation, fluids are matter, and all matter has mass, yeah, okay? All matter has mass. So if an object is gaining fluid, it has to be gaining mass, and it isn't, okay? When I pull that object that was cold out of the hot water, it's just hot. It's not heavier, Okay, so this now is not only an invisible fluid that I can't see, it's a massless fluid that I can't measure either. Okay, that's where people are like, come on, man. It's not magic. Come up with a better explanation. Except that you can't. Energy really is something that flows from one place to another without transferring any matter. Okay? It goes through matter, but it doesn't move the matter itself. Okay? From one, well, I mean, it can if it's an object, but it's not going to make an object heavier. Okay? So his ideas became the principles of what we call thermodynamics, movements of energy. Right? Dynamic means to change. Thermo means heat. So changing heat or changing energy. Okay? Okay? His idea of energy flow was actually fairly well accepted, but not the invisible fluid part. Okay? This idea revived this whole idea that atoms move, okay? And movement of atoms was how energy gets transferred from one place to another. Okay? So transfer of thermal energy from a hot object to a cold object, that's heat. Okay? That's something we need to understand. Transfer of mechanical energy from one object to another is work. Transfer of thermal energy is heat. Okay, so now we understand how heat moves from one place to another. What we have to understand now is, can I make heat and mechanical energy turn into one another? Well, it's pretty obvious that mechanical energy, movement, can be turned into heat. Okay? Because there's always what force there? What force always turns mechanical energy, like movement, into heat? Resistance starts with F. It is a force. Friction, right? Okay? The force of friction is resistance. Okay? Friction is usually what resists you. Gravity can resist you as well. Okay? But friction is a common form of resistance. It's what happens when two surfaces are pushed together and have to slide past each other. Okay? That is always going to result in the loss of energy as sound and heat. Okay? So, what Benjamin Thompson discovered was that you could make heat from mechanical energy. Okay? Now, the way he discovered this was, for some reason, he changed his name to Count Rumford. I don't know why, but he did. Okay? He became the Minister of War in Bavaria, and his job was to supervise the construction of cannons. Okay? You make cannons by taking a big lump of metal and a drill. Okay? And I don't mean like a little drill. I mean like an auger-sized drill that is people-powered. Okay? So there's a bunch of people turning this auger by its handles, and they're boring into this big lump of metal to make a tube. Okay? The tube is essentially, they're rifling this cannon. Okay? Well, it's not strong enough to contain the explosion usually. When you melt something and then reform it, those metals usually weren't, at that time anyway. We didn't have the smelting abilities, right? Okay? So they would bore this thing out. When they were boring it out or rifling it to make the barrel smooth, it would get really, really hot. So Count Rumford is also responsible for the invention of the coffee break. Okay? Because what these guys would do while they were working is they would put a tea kettle on the cannon, and then they would start turning. And after a while, they could boil the water. Okay? They could boil the water in the kettle, okay, by converting their mechanical energy into heat. Okay? There was that much friction and heat produced from what they were doing. So if they could get the water to boil, they could make tea, they could take a break. Okay? And it made sense because if they kept boring, it might get hot enough that it would warp. Okay? And if it warps, then the cannonball doesn't get out of the tube right, and that doesn't work out well for the people firing the cannon. Okay? They want the cannonball to get out of there quickly. Okay? So that's what he discovered. He discovered that you could turn mechanical energy into heat and that the two were related. Okay? And that was an important discovery. Okay? To know that those two are related, because it is possible to go the other way, just not efficiently. It happens naturally one way. Okay? It'll happen the other way too, but not very well. Okay? All right. So Rumford suggested that heat could be manufactured by the motion of his workers. In other words, mechanical energy can be turned into heat. Okay? Yeah. The supply of heat was the supply of heat was endless as long as the workers were turning the drill. As soon as they stopped, then the cannons would cool off. Okay? Where are the workers getting the mechanical energy from? From their muscles and the food they ate. Food they ate, changing the shape of the muscles, turning the thing. All right. Now, a little bit later than that, Thomas Young, okay, English physicist, he linked mechanical energy, okay, to this idea of kinetic and potential energy. He's the one who essentially discovered that equation I just wrote on the last page, EM equals EK plus EP. Okay, all right. So the idea here is energy is the capacity to do work. Okay, and Young discovered that an object could have both potential and kinetic energy. Okay, the guy that came before him, Leibniz, he understood that an object could have energy, but he thought it could only have one or the other. He didn't realize they could have both at the same time. Because with thermal energy, you can't change both at the same time. Okay, but with mechanical energy, you can. All right, most important scientist there is related to energy is Joule. That's why the units for energy are joules. Okay, if you do something great, you get the units for it named after you. That's why the units for force are newtons. Okay, do good things, you get rewarded. Okay, so what Joule showed was quantitatively, that is measurably, that mechanical energy and heat were related. Everyone else was showing qualitatively, hey, look what happens when this is going on. See, it gets hotter. But they couldn't show a mathematical relationship kind of between the two or show that this much energy was turned into this much energy. But Joule did. Okay, and the way Joule did that is he converted potential energy into heat. Okay, and the way he did that is the same way that you or I could do it. Okay, if you go home, you take a hammer and a piece of wood, not something good, not the the railing handles or things like that. Like take an old piece of 2x4, okay, and just pound on it for a while. Okay, just hit the same spot on that piece of wood, like 10 or 20 times. Put your thumb there. It'll be hot. Okay, because you can turn potential energy or mechanical energy into heat. Okay, very, very simply. So he showed that with his falling block apparatus. Not rocket science. Okay, he had two big blocks of wood. Okay, and he had a thermometer in this block that was stationary. So what he would do is pull the falling block up and away, doing work, same as Newton did with his Newton's cradle, giving it potential energy. Then he would drop it. Okay, and when it came and smashed into the stationary block, the temperature of the stationary block would jump. Okay, only explanation for that is that that there was energy in this object. He proved it quantitatively. Okay, the energy of this block went up. The only place it could come from was this block. So he proved potential energy is a form of mechanical energy that can be converted into thermal energy through a collision. Okay, he had another apparatus that did a similar thing. He had a thermometer in a jar filled with gas with these little like fan blades inside, and he had these falling masses. When they would fall, it would spin the blades inside. Okay, and as those blades would spin through the gas inside, the gas would heat up. Okay, again, showing that the energy here, because of their position, or it showed that there was energy in these masses because of their position above the ground. As they fell, they converted it to other forms. Because you couldn't quantify that, right? Like I can't go, okay, I've got, how much energy did I use when I rubbed my hands together? It's hard for me to calculate that. It's also hard for me to calculate the change in thermal energy by measuring the change in temperature of my hands. Whereas with this, okay, he knew the heat capacity, which we'll talk about in the last unit of these blocks. And he knew he could measure the temperature change and calculate the energy gained by this and relate it to the energy lost by this. Okay? Everybody with me there? Okay. All right. I want you guys to answer the circled questions. Pardon me? Yes, it did.